Hey guys, it's Mr. Sheelan here. This is going to be the Unit 8.3 notes lecture video concerning electron configurations and orbital diagrams. So, alright, we are basically covering, this is the last material for this year of school year 2021. So let's get to it. So remember, what the whole point of talking about electron configurations, to figure out the shapes of these atoms, it all comes down to pretty much the valence electrons. And remember, the valence electrons are the outermost these are the outermost energy levels of the atom. And if we know what the outermost looks like, and we know how many are out there, excuse me, my goodness, and we know how many are out there, we can get a sense of just what kind of characteristics they may show, okay? Because there's some trends between them all as far as where we think the electrons are located, or at least possibly located at any kind of percentage or with any kind of probability. So, okay. Now these electron configurations and orbital diagrams, that's what we're going to be making here, are a bit wacky. This is going to be a bit, how to put it, super confusing. Only because it doesn't make a whole lot of, at first it doesn't make a whole lot of intuitive sense. At first it doesn't. Once we kind of get into the motion of things, hopefully it'll make sense. Now, the reason for its non-intuitiveness are basically because of, is because of this, I should say, is because of these three rules/principles. So here's what we have to follow when we make these diagrams and these configurations. We have to follow what's called the alpha-bow principle, the Pauli exclusion principle, and the Hund's rule. Okay, so the alpha-bow principle states that electrons are added one at a time to the lowest energy orbitals available until all the electrons of the atom have been accounted for. So basically this is going to tell us that we have to continually go to a lower energy level before we pop up to a higher one. Okay, because that just makes sense. When you think about it for a second there, remember, naturally the world wants to move in such a way where it can expel and use as little energy as possible. And so alpha-bow principle is saying that, well, electrons are going to want to fill in the easiest places first, the lowest energy levels first. Then we'll pop up to the higher energy levels. Okay? So that's really what the alpha-bow principle is saying, is that don't start from high to low. You got to go from don't go from low to high. You want to first fill into low. So you do want to go from low to high, I guess. Sorry, my brain's getting confused with diffusion at the same time here. So that's what the alpha-bow principle states. The Pauli exclusion principle states that an orbital can hold a maximum of 2 electrons having opposite spins. Now, simply put, the spins we've really never talked about the spins, and we really won't get into the details of what the spins are. Roughly speaking, the spin is more or less its magnetic orientation. The electron's magnetic orientation inside of a particular orbital. That's all it is. Which to me doesn't sound a whole lot, because I can picture it. Maybe for you it's a bit concerning and confusing. We'll get to what that means when we get to the orbital diagrams. But it's basically this Pauli exclusion principle is pretty much just saying that because electrons are both negatively charged, there's got to be some sort of way that they can be somewhat close to one another without just pushing each other away. And that's kind of what Pauli exclusion principle talks about. It's like, oh, well, they're going to have different magnetic kind of orientation so that they're not bumping into one another, and also all kinds of other electrons found in other orbitals on an atom. And then there's Hund's rule, and Hund's rule is really, we're only going to see that when we start putting the orbital diagrams together. This is where electrons occupy equal energy orbitals so that a maximum number of unpaired electrons results. Okay, so this is to say that it's to say that we're going to be filling up one particular spin, and then we're going to start filling another particular spin when we get to orbitals. And again, that'll make more sense when we get there. So let's just get straight to making the electron configuration, understanding how we go from lower energy levels, then higher, and then higher. because it's not terribly obvious how we do that. So we're going to create a chart showing the order of the electrons that fill the sublevels. Okay, so here it's already been made for us right here, and it's going to kind of already skip basically this first step here. So using this guy right here, this whole chart, we know that as we go through primary sublevels, we're going to increase the orbitals. So meaning we're going to go from 1s, and then it's going to go then 2s, and then 3 primary, principal energy level. Here's 4 principal, 5 principal, 6, 7, 8 principal. So these numbers indicate the principals. Okay, the principal energy level. Yeah, and then next to them you'll see are the orbitals themselves. So here we got 2s, we've got 2p, 3s, 3p, 4s, 3p, 4d, 4f. So we kind of see this pattern going on in how we lay this out. We've got principal energy levels, and then in the rows we've got the orbitals. Now, if only we could read it from left to right like this. And we're not going to be able to read it like this. We're going to read it like this. We're going to draw diagonal arrows through the sublevels from upper right to lower left. And I'm going to do one even more, just so we don't get confused here. We're going to first circle all of these, because I think circling them, it makes it a little easier to understand how to read this, or it helps us to better read this in the future, because this is going to be a super duper handy dandy tool that you'll be able to have throughout practicing this. Okay, so we don't read it from left to right like this. The way we read it is actually from top right to bottom left. Okay, so we're going to draw these diagonal arrows just like this. So this is how we read this. Okay, this is how we go from fill in that low energy level, fill in the next lowest energy level, fill in the lowest next lowest, the next lowest, and then we do this. Okay, this is how we read this. Okay. If you have a ruler, the ruler is going to be way better, you know, obviously, to make these straight lines so it doesn't look so bad. Okay, so it's just like that. This is how we're going to read it. So here's the first line to read. This is the second line to read, the third, the fourth, the fifth, sixth, seventh, eighth, 9th, and 10th, and then the 11th. And here, I'll even add in a little note. So, order to fill and read. Okay. So again, this is the first line we've got to fill. This is the second line, the third line, and it's in the order. So it's also in the order that we have to read these. And we're going to use this to properly designate the electron configuration of a particular atom. So, okay. So this is, again, how we're going to read this, guys. So electron configuration is, basically, it shows the distribution of electrons in the sublevels of an atom. Okay. And, excuse me, when we put these together, we've got to use this dude right up here. And we've got to make sure we're reading it properly in order to get this done correctly. So, number one, what we have to do, figure out how many electrons the atom has. Okay. Then we start right here at 1s. We're going to write down 1s. We're going to put the maximum number of electrons that are going to be found in the sublevel. And it happens to be for 1s, we can only hold 2, because there's only one orientation of that sublevel. So, and then now the question might be, okay, well, that's cool. I understand that that one's 2, but what about, you know, P? What about D? Well, that's where the 8.2 notes come in. So looking, this is the second page of 8.2. This is what we're looking at here. So it's the maximum number of electrons per the orbital shape. So S, no matter what the S is, the maximum number of electrons it can hold is 2. For P, the maximum number it can hold is 6. D is 10, F is 14. Okay, F is 14. So if you land on, say, 3p, well, 3p can only have 6 max electrons, so it would be 3p6 if you're able to fill in the whole thing. But we'll get to maybe I'll get to explaining that a little bit better here in a bit. Okay, so you're then going to subtract the number of electrons in the sublevel from the total. So if you've got a total that you found in number 1, you put down 1s. Well, now you've just filled in 2, so it'll be whatever your number of electrons is for that atom minus 2. Okay, and then you just keep doing that for every orbital you're filling in, every orbital and energy level you're filling in. You're then going to follow the little arrow to the next sublevel. If you come to the end of the arrow, the head, you're going to go back to the tail. So let's say this. So here you go from 1s, you're going to go this way, and then you're going to go back to the tail up right here, read this way, back up, just like this. Okay, just like this. Okay. And you're going to continue this until all the electrons have been put in the sublevels. Okay. So, and then the last step here is going to be the final sublevel may have less than its maximum possible electrons. So if you run out before it totally fills, okay, in this case, just write the superscript with however many electrons are left. Okay. So it looks like this. So if we were to use bromine as an example, okay, well, bromine has 35 electrons. Okay, and then this is what its electron configuration is going to look like. Okay. Here, let me zoom in on that right quick. So this is what its electron configuration is going to look like. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Okay. Maybe for some of you that's super obvious how we got that. I'm feeling that most of us were sitting there kind of scratching our heads and going, huh? What? So let's do one. Let's kind of do a practice here. So let's say, because this is how we're going to practice this, let's say I give you sulfur. So as an example here, I'm going to say, all right, give me the electron configuration of sulfur. Okay, so you're going to look at the periodic table. You're going to find out the number of electrons that sulfur has. And sulfur happens to have 16 electrons. And the way that we know it has 16 electrons, remember, is we look at the atomic number. So the atomic number is the number of protons. And if it's a neutrally charged atom, which this one is because it's not an ion, a neutrally charged atom should have the same number of electrons to protons. So if it has 16 protons, it must have 16 electrons. Okay. We're then going to do this. We're going to say, okay, EC for electron configuration. And we're going to say there are 16 slots that can be filled in with electrons here. So we're going to do this. We're going to start with 1s. And we are then going to put 1s2 because there's more than 2. There's 16 slots. Okay, and we're going to kind of keep track here. Let's see, try to find a spot that I can put this without a nasty glare on it. Oh boy. Here, or I can do this too. Need to kind of just angle it a little bit to see if that's enough. Nope. How much is enough? Oh, quite a bit. Try to put my phone behind it real quick. That ain't too bad. Okay. So, alright, sorry about this. Okay. So, we're starting with 1s. And again, we're going to keep track of, we're keeping track of how many electrons we have left, how many electrons that we still have to fill here, or that we have to use up. So, okay. 1s2, okay, 16 minus 2, there's still 14 slots left. Okay, so then we go down, we go from here, then we go down to the next energy level, 2s, and we can only fit in 2 there, so then it's going to be another minus 2. Okay, we got 12 left. Okay, 2s, we're going to go back up to here, and then to 2p. Okay, now remember p, it can hold more than 2. P's can hold up to 6 electrons. Okay, so we still have 12 left here. So we can put all 6 on there. So 2p6, we're left with 6 now. And then from 2p, we're going to go to 3s. and then the s's can hold 2, so minus 2. We're left with 4, so we're going to go from 3s up here to 3p. And then 3p can hold 6, but we only have 4 left. So instead of trying to distribute this any kind of weird way, p can hold 6, but it doesn't have to always hold 6. So we're only going to write down what's left, which is 4. Okay. Now we can double check that real quick just to make sure we have the right amount of electrons shown. So 2 plus 2 plus 6 plus 2 plus 4 gives me 16. And I definitely have only 16 electrons in sulfur. Here is the electron configuration for sulfur. All nice and done. All right, let's do maybe another one. Let's maybe try out let's try calcium. Okay, so we're going to try calcium here. So calcium, looking at the periodic table, is going to have 20. It's going to have 20 electrons. Okay. Kind of position this so we can still read everything. Okay. Now, what's cool about this is that we just did sulfur, and we know that sulfur has 16. Instead of having to kind of redo everything in our brains and all that kind of stuff, we could actually just look at sulfur and say, hey, sulfur had 16. Calcium has 20. I can just rewrite most of this and know where I left off. So here's 1s2, 2s2, 2p6, 3s2. Now, up to that point, though, that right there is 12. Okay, so because I know this, so 20 minus 2, minus 2, minus 6, minus 2. So I still have 8. So I can throw all 6 on there. Cool. So minus 6. Hold up, 2 plus 2 plus 6 plus 2 plus 6 minus 20. So I still have room for 2 here. So I've got room for 2, so I'm going to put, looks like the next designation, so from 3p, looks like we go from 3p to 4s, and so I fill in 4s. And there's only 2 left here, and I can put 4s2. And then I have my electron configuration for calcium. Easy peasy. Now, that's just electron configuration. Okay, just electron configuration. The next kind of bit that we have to figure out is we have to then, after we have the electron configuration, we have to know what the orbital diagram is going to look like. Now, the orbital diagram isn't going to be like this weird hodgepodge of tossing together all of the orbitals that a particular element has. It's basically just, all we're showing is we're showing the electron configuration mixed with the spins and number of electrons physically that should be on each orbital. Okay. And it's the distribution of electrons among the orbitals in each energy level and the sublevel in an atom. Okay, and it still follows those 3 principles we talked about on the front. The Orbital principle, the Pauli exclusion principle, and then Hund's rule. And this is, where we're going to see Hund's rule. Okay, Hund's rule is going to kind of show this here with how we distribute our spins. So, first we got to figure out the number of electrons an atom has. Okay, which in the problems that we're going to complete, or the practice that you're going to do, you're going to be told to find the electron configuration and also the orbital diagram. So you're already going to have the number of electrons. That shouldn't be a problem. But if you don't, you still have to find them. Okay. We're still going to start with 1s. And really, these steps are somewhat. Most of these steps are like half the steps are pretty much as if you're, tasked to just show the orbital diagram without having the electron configuration. If you have the electron configuration, this is like no problem whatsoever. But anyway, so start with the arrow at 1s, write the sublevel, and put blank lines over it representing the number of orbitals. Okay, within the sublevel. Really, what this should be is write the blank lines first, the number of blank lines you need for each orbital, and then write the number with the energy level with the orbital. Okay, and I'll show you why in a second here. Okay, you're then going to put the electrons down, and you're drawing the electrons as arrows, and this is where the spins come in. So there's up spin, down spin, which really is just, you can think of it almost like, is it positively charged, is it negatively charged, like a magnet, similar to something like that. Okay, you're going to draw those arrows onto the blank, the orbital blanks, based on 3 principles. So 1 electron per orbital, until all orbitals for a sublevel have 1 electron in them. So that's the Hund's rule for the most part right there. Fill the orbitals with a second electron with the opposite spin. And in this case, we always start with up spins and we finish with down spins. Okay. Once all orbitals within a sublevel are filled, subtract the number of electrons used from the total and go on to the next sublevel based on your chart. Continue filling the orbitals in this manner until all electrons for the atom have been used, and identify the number of unpaired electrons. And here's an example still using bromine. Okay. So, excuse me. So here is what here's what the orbital configuration looks like for boron 30 or boron 80. This is right here. Okay, it's this dude right here. And we see here that it's going to have 1 unpaired electron, and that 1 unpaired electron is this guy right here. Okay, but this is what we're doing. This is what we're putting together. So let's use calcium. Let's just keep using calcium, and we'll use both calcium and sulfur. So calcium here, just a reminder, it has 20 electrons. And not only that, we're going to rewrite the electron configuration real quick. So calcium's electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, so there is the electron configuration for calcium. Now, this is why having the electron configuration is super handy, is that when we make the orbital diagram here, we can just look up at this dude, see what we have to fill out, and then fill it out correctly. Okay, now I've got my electron configuration. I'm now going to start writing out all these little lines. Now these little lines, though, again, are going to show us the orbitals, and I'm first going to kind of showcase them over here as to what they should look like. So 1s is just a single line. Oops. 1s is just a single line because only 2 electrons can fit in there, and only 2 electrons can fit per line, right? So 1s would look like this. Now this is not in order. I'm just like showing if it was p, because this could be any p. Any p is going to be 3 of them. Okay, and you'd fill it out like so, up spins and down spins. Here's 3D, 1, 2, 3, 4, 5, and then you'd fill them out like so. Okay, now again, this is not for calcium, this is just showing you what you do. And then there's lovely F, lovely F. So 1, 2, 3, 4, I'll put a 5th one over here, 5, 6, 7. Okay. So F's have 7 whole lines, and you can fill every single one of those lines with 2 electrons. So this is what we're doing here as far as these lines go. So looking back to OD, we're just going to follow the electron configuration and say, okay, we've got 1s, 2s, 2p, and all these guys up until this 4s2 are filled. So we can just do this. It's a whole lot easier to write the lines first and then write these guys down. Write the energy level with the sublevel, or sorry, the orbital. Just because when you get to like P or like D's and F's, I know that for myself, if I write like 4F, and if I don't space these lines out, I'm gonna have like this I'm gonna have these like itty bitty little teeny tiny guys, and then these like big lines. And then these little itty bitty teeny tiny ones, I gotta really fit in those guys compared to those lines, which can fit them all pretty easily. And it's just personal preference. It's a whole lot easier to go, same size of line. Let's see, 1, 2, 3, 4, 5, 6, and then place it down in the middle. Okay, just way easier. And plus, you don't have, you kind of not force yourself to use itty bitty little lines. So anyway, there's 1s, 2s, 2p, 3s, and we can drop down since there's really not a whole lot of room. We can drop down, that's fine. 3p, and then there's 4s. Okay, now we gotta look at the numbers that are up here and see how many we can fill. Okay, 1s, 2s, both of these guys can have are gonna have 2 electrons. Now for 2p, this is how I'm gonna fill it out because this is the habit you should get into. You should fill it out first by drawing the up spins and then drawing the down spins. Okay, and when we look at sulfur, it'll make sense why. And really, I shouldn't have put that guy there. I should have started over here because we got to fill left to right in first before we go over here. But I knew that this was going to be filled anyway. But all right, and then 4s, simply put, it's all everybody's filled up here. It is a nice crowded family. And then we have to identify the number of unpaired electrons. And there are none. There are 0. And you'll see a decent number of zeros while we're practicing this. It is okay to have unpaired electrons. You do not always have to have unpaired electrons in this. So, okay. Now, do sulfur. I was kind of losing my train of thought there. So now to try to do sulfur. So sulfur, so to rewrite sulfur's electron configuration, it's 1s2, 2s2, 2p6, 3s2, and I'm running out of room, and then 3p4. Okay, so its orbital diagram, it's going to look something like this. So 1s2, 2s2, 3p6, 3s2, and then 3, oops, this is supposed to be a 2p, not a 3p, my bad, 3p4. So we fill in the spins. Now, okay, this is where we want, this is where we want to have this habit of filling in up spins first, then down spins, because here 3p is only going to hold 4. So we're going to go 1, 2, 3, and then come over here and then fill those from left to right. Fill in 4. And then identify the number of unpaired electrons. And this guy happens to have just 2 unpaired electrons. Easy peasy. So, electron configuration, orbital diagram right here, unpaired electrons. This is what we're doing because what this tells us is this can tell us about a whole lot about the element. It can tell us like if its proclivity towards taking in electrons, not taking in electrons. It shows us the proclivity or not the proclivity, I should say, but the arrangement, the theorized arrangement of these atoms, all that good stuff. So that's it for the most part for these notes, guys. As a challenge, what I want you to do on your own, I want you to make the electron configuration for, and also the orbital diagram for thallium. So do that yourself. I'll make a little short video walking you through what thallium should look like because it's a long one. And I'll get that out as soon as I can. So that's it for the notes, guys. So if you have any questions for me, make sure you ask. If not, I'll see you in the next one.